We're now going to take a look at organometallic reagents and how they react with carboxylic acid derivatives. So what are some of those carboxylic acid derivatives? We have esters, we have acid anhydrides, and we also have acid chlorides, What are some other ones? Esters, anhydrides, acid chlorides. We have amides. All right. So we want to take a look at how the organometallic reagents react with those types of carboxylic acid derivatives. Now, one thing that we need to understand is I'm going to represent these and even carboxylic acids. Okay, like in general terms, I'm going to kind of represent it like this. We have a leaving group. And just to get you a better idea of what I'm talking about, like if we wanted to look at an acid chloride, we would just replace that leaving group with a Cl. And if it was an ester, we would replace that with a OR type idea here. And I'm using general terms because the mechanisms are very similar for all of these things. And so before we tackle how organometallic reagents react with carboxylic acid derivatives, let's remind ourselves how it reacts with a simple ketone. And so an organometallic reagent that we could look at would be, let's say, a Grignard. And probably let's get rid of that Me and just put it CH3. All right. Like that. And we can translate a Grignard reagent simply into this guy, that negatively charged species like that. And so what is the product when we take a ketone or an aldehyde and treat it with a Grignard reagent? Eventually, we are going to get to this. We generate an alcohol. We added our CH3. So that CH3 coming from the Grignard is that guy right there. And we make an alcohol. All right? But now compare and contrast. The blue marker's not showing up the best, is it? Let's try this one. What if I change that ketone right there into, let's say, an acid chloride? Or not turn into, let's just compare a ketone versus an acid chloride right there. And we treat that with a Grignard. Look at the difference here. We still generate an alcohol, but look at what we added. We added this CH3 right there. We added it to that carbonyl carbon twice. But in a ketone and an aldehyde, we only added that to that carbonyl carbon once. And the difference between a ketone and an aldehyde versus the carboxylic acid derivatives is the fact that we have a leaving group. And that leaving group is the difference. And that leaving group allows us to add the Grignard or the organometallic reagent twice. So before we get into the mechanisms and the nitty-gritty of all this, let's just establish some ground rules of what we're going to be dealing with. Okay? So the first two organometallic reagents that I want to look at are the Grignard. Okay, so we'll represent that like this, an RMGBr. So Grignard right there. And then alkylolithium reagents. Okay, so these two reagents, we also have the dicuperates or the Gilman reagents, but we're not going to look at those quite yet. I just want to look at these two right here, okay? And remember that both of those can simply, when we simplify it down, can just be represented by a R minus. Now, these two reagents, they can react with esters, anhydrides, acid chlorides, but they do not react with amides very well. And so typically we just don't do it. And they do not react with carboxylic acids. All right? So let's first go through the mechanism, a general mechanism of how these organometallic reagents work. So I'm just going to put a leaving group here, and that leaving group is going to represent these three types. And then we have what? We could use any one of these, Grignard or alkyl lithium, which simply represents, can be represented as an R minus. And so we can come and bring that in, pop that off like that. That will give us this species right here. There's that R group. Now look at what can happen here. Is that this is a tetrahedral intermediate, and that can collapse back down, kicking off the leaving group. And so we would generate this species right here. And what did we just generate? We generated a ketone. And we already know ketones react with organometallic reagents. So it's just going to do it all over again. And it's going to come in, do that. And then we generate this species right here. I want to differentiate that R right there. So I'm going to put a little symbol right there. And the R without the little line right there is going to represent the organometallic reagent. Then we have the alkoxide, negatively charged oxygen, another R group, another R group. And so what are we going to do? With this species, we're just going to do a simple proton transfer, an aqueous workup, or an acidic workup, and that's going to convert that right there into our alcohol. And we'll draw our little proton transfer right here and draw our final product down here, shall we? Like that. So that's one way to generate a tertiary alcohol. So let's make sure we understand each step here, what's going on here. So this is our nucleophilic addition step right here. Nucleophilic addition step. And then this one is our nucleophile elimination step. And then we're going to do another nucleophilic addition step with the ketone, get us this thing, and then we do our proton transfer. So that's the generic mechanism that works for these three right here. Now let's talk a little bit about why amides don't work. Because when you go back to my analogy of these carboxylic acid derivatives and where they are on the rungs on the ladder, amides are very low. They're just not reactive enough. So we just don't deal with them typically. Carboxylic acids, on the other hand, have a different problem when you try to react carboxylic acids with organometallic reagents. So let me show you the issue that you're going to run into if you try to do this. And hopefully you see why it just doesn't work. The reason why it doesn't work is if you have a carboxylic acid and you treat it with a organometallic reagent, R minus here, you might hope and want it to come in and do your nucleophilic addition step. That's what you want to do. But it can't do that. And the reason why it can't do that is because we have a very acidic proton. So this is not going to act as a base, or it's not going to act as a nucleophile when there's an acid present like that. And so what would actually happen is we'd get this reaction, or simply a proton transfer here, and generate this, our carboxylate, and then the reaction's dead. That's just where it stops. Okay, so organometallic reagents don't go with amides or carboxylic acids. So in the next couple videos after this one, let's go through some examples of the organometallic reagents with some of these functional groups, so you can have a better idea of seeing what it looks like in a practical way.